So welcome everybody. It's great how many people are in this room. So this will be truly a fun talk. So we'll enjoy ourselves. This is what I'm promising. I'll be talking about taming the performance beast. We've heard about a lot of beasts in the past few days. So you still have this vivid image of fiery dragons. So in this case, it's not a dangerous beast, it's a tricky beast. So I believe you're all here because you care about performance, because you have experiences with performance, and because you've made the experience, it's not particularly easy to get true performance out of the system. Although C++ is renowned for being a fast programming language, it's not just like you can write everything and the compiler will magically turn this into something that is truly amazingly fast. Unfortunately, this is not the case. So it's a tricky beast. We'll try to tame it a little bit. So this is not, of course, dealing with every single aspect of performance. What I try to provide you is a piece of the puzzle to, tame the beast a little more. So what I will focus on is data structures. In 2014, Chandler gave a talk called Efficiency with Algorithms, Performance with Data Structures. The essence of this talk is, if you want to be efficient, choose the right algorithm, which minimizes the amount of work you're doing. If you truly want to go into performance, choose the right data structure. And this is exactly what I'm trying to do. We will be dealing with choosing the right data structure for common tasks. So, just a warning right from the beginning. This is kind of an interactive talk. I was not expecting so many people to be here, but it still will work out. So, don't be scared. All you have to do is, at some point, raise your right arm. And if this right arm is not available, use your left arm. And if you're particularly into a particular answer, use both arms. I don't care. So, let's see how this works out. So this also is about estimating performance. You usually have a gut feeling, okay, this is fast. This is not so fast. But unfortunately, our gut feeling is not the most exact one. So it fails us more often than it's actually leading us to good performance. So this is why you will be estimating performance. Yeah, you will train this feeling, you will get a feeling, okay, is my gut feeling good or is it not so good? Okay, this, of course, data structures in abundance. To make it simple, we're just focusing on the standard containers because there's already a whole bunch of containers available. It's perfectly enough to take a look at what the standard delivers us. When should I use which standard container? Huh? All right. I know what you're thinking. Basically, we have all the information already. There is plenty of advice when to choose which data structure. For instance, this is something that you can find somewhere on the internet, kind of a decision graph. So I'll give you an example. Is the order important? Well, I say no. Do you need to find an element by key? Well, in my particular case, yes. Do I allow duplicates? No. Store the key, store a key separate to value? Well, no. And I end up with a set. So in this simple decision graph, I realize in the end, I should use a set to truly get the best out of my system. But this is truly something that will help you get the best performance. You hopefully have a feeling, not really. This is not real scientific, based on some performance results. Okay, but you get the point, yeah? And there's a lot of decisions, and eventually you will end up with all the containers from the standard. So this is the old standard, of course. This more advice. So everybody of you know Scott's, have read Scott's book, and so you've encountered this advice from one of his books. Do you need fast traversal of your elements? Well, use a vector, a deck, or a string. Do you need insertion, erasure only at the back? Well, of course, use a vector or a string. Do you need insertion, erasure at the front and back? Of course, use a DEG. Do you need to frequently insert, erase in the middle of the range? Use a list. Do you need to be able to insert a new element at an arbitrary position? Use a vector, DAG, list, string. Very accurate here. You need to search frequently. Is lookup speed a critical configuration? Use a hash container, a sorted vector, set, map. It sounds like good advice, but this is truly giving you best performance in all situations. So, for instance, is a list truly the right data structure to frequently insert in the middle? Depends. And this is exactly the point. So this may be good advice, it might not be. Of course, there's also other publications. Matt, a couple of years ago, wrote a paper about set. When should you and when should you not use a set? And the advice is basically driven by logarithmic complexity. So if you need to find something, and it's a huge collection, use a set because it has logarithmic complexity. So the term complexity is used very often. Yeah? So the big O notation. We'll come back to this. Okay, essentially what I want to do is, what I want you to do first is to completely forget about this kind of decision graphs, this kind of advice. This is probably not going to get us anywhere. So forget about this. We'll try to come up with something better in the end. Similar, but better. All right. Before we start, let's very quickly recap the standard containers. Just to load them in our short-term memory, we'll need this knowledge, of course. So a vector, well, of course, a vector is basically an array. It is an array because the standard guarantees us that the elements are stored contiguous to each other, and the array is the only data structure that gives us this property. A list, well, a list is a doubly linked list. Individual elements that are linked together such that they can move forward and backward. The important property is that every element is allocated individually. I add an element, I do an allocation, I copy the value in the node. If I remove an element, I delete the according node. Has some nice properties, so a list might have stable nodes. A DAG, hopefully everyone knows what a DAG looks like. It's probably one of the mostly ignored containers. A DAG is kind of a mixture between a list and a vector. A little bit vector, a little bit list. The property of a DAG is that I allocate a bunch of elements, and since it's supposed to be performant, this block of elements has the size of a memory page. So I can load a page very quickly, I can address one page, but the pages, also these memory blocks, are connected by some kind of list-like data structure. Yeah? Set and map, well, obviously tree-like data structure. So binary trees, I can move forward and backward throughout this tree. All of the trees have, of course, additional pointers. I can also go to the parent element, so I can traverse the entire set or map for this matter. I will only use the set, though, because a map is only an additional value associated with the according key. It doesn't really give us additional insight. It's just a little more memory that I have to load. So set should suffice to put the tree data structure to the test. Okay, and then there's one more that I want to use. This is, of course, the C++11 data structure, the unnoted set, which, you might wonder, looks like which other container? Well, depends perhaps a little bit. You will see that it mostly resembles a list, of course, with an additional governing data structure that makes sure that we can very quickly go to a specific element. So these buckets basically give me direct access to a specific element in the list. All right. A short disclaimer also, because there's a couple of things this will not be. So this is not a battle of compilers. So I will use one compiler, and this should be completely sufficient. Different compilers might give you a little bit different results. From a qualitative point of view, it should be equal. So the factors might not be exactly the same number, but you should get a fairly good idea. This is also not a battle of operating systems. I don't care which OS you use. I just used the laptop I had. Also don't have the time, unfortunately, to compare data types, so I'll restrict my benchmarks to integer, which is, of course, a fairly simple data type, but basically the integer represents everything that is built in, of course, and everything that can be copied cheaply and or moved. Yeah? Everything that is expensive to copy, cannot be moved. Okay, this is unfortunately not part of this talk. Also, I do not take special allocators into account. I will just use the standard allocator, which basically uses new, of course. Special allocators can entirely change the results. This is something that you're aware of, so, well, if you have specific requirements, use a specific allocator and just benchmark and profile accordingly. And this is, of course, also not the ultimate answer. It gives you some qualitative feeling for performance, but not the use this for every, use these guidelines for everything that you do from now on. All right, so ready to tackle the first benchmark, which is, first the things that I use. So I use the Apple LLVM, a CPU of 2.6 gigahertz, and of course a couple of flags that make sure that we truly achieve the performance that we want to have. All right, now, the first benchmark, a boring one, traversing elements. So we have a container filled with elements, and all we care about is traversing this container from the first to the last element. Yeah? Basically, it's simple. So I have a loop that traverses all these elements. I do something with the elements, else the compiler is basically removing the for loop entirely, so I don't measure anything. I just sum these integers up. It doesn't really spoil anything. I do this a couple of times. You also saw in Chandler's talk that you cannot just measure something once and you're done. You have to truly keep this running for some time and then, of course, create an average. And so this is what I'm timing and what I'm measuring. Okay. So the first question is basically too simple to pose at you. Which container would you consider to be the fastest for this particular benchmark? So, of course, it's the vector. Yeah? Vector will be the baseline in this particular benchmark. The really interesting question is, what is the performance of the other containers in relation to standard vector? So, let's take a look at DEG, the double-ended queue. You saw, okay, it has vector-like properties, but it's not quite a vector. So, from a gut feeling, what do you think is the performance just traversing the elements? So from very small DEGs to DEGs that's called 100 elements. So is it a factor of, let's say, 1.1, so very close to the vector? Okay, this would be about half of the people. Who feels, okay, there must be perhaps a little more overhead. So it's not that simple to traverse the DEG because I have intermediate gaps and I have to mind those gaps, else I have a problem. Who thinks it's perhaps a factor of 2? Okay, this would be about 1/4. And the rest thinks, it's probably more expensive. Factor of 5. Okay, who feels it's even more expensive? Okay, no one. No one dares to go beyond 5. Okay, to keep it a little more interesting, I do not show the result just yet. Let's talk about standard list first. So standard list is something that you realize is, well, difficult to estimate. Well, I find one element, or I have one element. In order to go to the next, I have to follow pointer, yeah, to the next element. In order to go to the other element, so the one after that, I again have to follow pointer. And this definitely bears some overhead. But how much in comparison to vector? So it feels, okay, it should not be that expensive. So it's also in the 1 point range. So let's say a 1.5. Okay, no one. No one trusts a list in this regard. So who feels it's kind of a factor of 2? Okay, this would be about 1/3. So I didn't quite. That's a good question. I'll come to that in a second, yeah? Okay. About 1/3 for factor of 2. Who feels it's more expensive? Factor of 5. Okay, this would be another 1/3 approximately, and the rest feels it's even more expensive, right? Okay, so let's take a look at DEG first. So the majority says it's very close to vector. This is also the gut feeling I had, and I was unfortunately disappointed. This is the performance of the deck. Unfortunately, I cannot really explain the spike, but it goes on and on in this linear fashion kind of forever. There is a factor of 6 in between. I guess this is something that you did not expect. I didn't too. The reason for that, if you take a closer look at one particular implementation, I didn't browse all of them, of course, is that it's truly not as easy to go from one element to the next. There's much more checking. Am I truly at the end of a block? If yes, I have to do definitely more work. Else, okay, I can go to the next element. These additional checks already spoil a lot of the performance that you can achieve, although you have a vector-like part. Yeah? A list, well, probably is even more expensive. And on this particular system, I got a factor of about 8. So this is close to 1 order of magnitude slower than a vector. Meaning if you choose a list and you frequently traverse this list, you've basically already lost about 90% of the performance. Okay, not 90, 80, whatever. That's surprising. So now there was the question of how did I add the elements into the list? Of course, this seems to make a difference. If you allocate all the elements in order very quickly after one another, then you would assume that the elements lie very close to each other. Remember, we are loading cache lines, and then the elements, well, I should load a couple of elements that are close to each other at once, and it should be faster. Yeah? I tried this. It didn't really make a difference. Not really. So, question in the back.
Is this measurements with cold or with hot cache? Do you iterate with the same elements all the time? Or
Yes, exactly. This is hot. So, I showed this before. There's thousands of iterations over all elements. So I traverse not just a single time, I traverse it 100,000 times. Yeah, so it's approximately 2 seconds that run the benchmark, and then I divide by the number of iterations. So the experience is, even if you have the elements very close to each other, it doesn't really make a big difference. So perhaps a factor of 8 becomes a factor of 7. The fact is the compiler cannot truly help you in optimizing this. There is not a lot of preloading as in the case of vector. This pointer arithmetic is very, very difficult, a question here. This is just the accuracy. So it is so fast that the accuracy drop is not accurate enough. I didn't try to make it a smooth line, though. I say this is qualitative results. If you use it on your system, it will be different anyway. So I don't really care about these things. So also this, I didn't have the time to really focus on why there is a performance rise here. But, well, it's an about factor. If it's 6, it's still very expensive. Okay, a set. Standard set is some in question?
Yeah, I have a question about the list, sorry, but it seems to me like the most important factor is like cache locality. So I'm just surprised you said that if I think if you have more cache misses when you try to find these things, and that would be the thing that impacts performance most.
Yep.
And then you said that's not the case. So I'm just wondering, do you have an explanation for that?
So it's always good if the audience discusses the topic, then I can go. Potentially, exactly. This is one additional disadvantage of the list. All the elements are somewhere in memory. And of course, you cannot vectorize this. And I said I add the elements. So the compiler has definitely much more potential for optimization. Whereas I tried not just addition. I tried a couple of things, and I found addition is just the simplest one, which gives me the result. So the factor is basically the same for all kinds of operations that you might do. That's true. That's true. Yeah, exactly. So this particular benchmark doesn't change. So I can also show you that it's with 100,000 elements, these lines just go on forever. This is to be expected to some extent. So Here it does make a difference. For the other benchmarks, it will. Let's take a look at set. Okay, you saw, okay, a set is definitely something that is very clever if I start at the top. Unfortunately, when I traverse the elements, where do I start? Not at the top. I start at the very bottom of the graph, so at the bottom left. Of course, at some point, I have to go a long way until I reach the next element. So no, it will not be below a factor of 8. What's your feeling? Is it really, 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 really more expensive? So who says it's a factor of 20 at least? Okay, majority still trusts in the set. It is a factor of 18, so close to 20. Yeah, so it is really expensive to traverse the elements in a tree in this fashion. This is what you should definitely never do. If you use a set, this kind of data structure, it is not for traversing elements, it is truly just for picking specific elements. Okay, an unordered set. This is probably one of the things that you wonder, okay, how will it perform? Which data structure will it resemble mostly? It has about the same performance as a list, which basically proves the claim that it is internally implemented as a list. So very close to list, a little faster this is measuring accuracy. Okay, the first lesson we've learned is if you really want to traverse your elements very often, you should consider using vector-like data structures. Everything else will give you a heavy performance penalty. Okay, also factor of 8 for the unordered set. Okay, the reason is basically very simple. You already said it. It has to do with cache locality. And I have to admit, I borrowed this slide from Scott and also from Mike. So I saw this before, but I still just love the slide. This is the best slide I've seen in years. So if you have some data in the level 1 cache and want to work with it, it's very quick to be loaded to some register. If you have something in the level 2 cache, yeah, it is still fairly fast loaded into the register. If you, however, have to load something from the main memory, this takes some time. Yeah? This is also one of my favorite slides because this is the opportunity to get something to drink safely without hurry. It's fun, isn't it? So, okay, it will take some time, of course. So there is a huge difference in performance between these memory hierarchies. So a main memory is just the slowest thing that you, okay, there's slower things, of course, but you do not want to really work with something that's in main memory. Eventually you have to, of course, but hopefully you have something to do while you're waiting. Yeah? And I have to admit something. So the visual impression gives you already the idea, okay, it's terribly slow. But this is still faster than I actually wanted it to be, because actually these presentation tools do not allow you to go beyond 60 seconds of animation, which means it basically should be a little slower even. Yeah, so, you want to see it again? Okay. So there's a factor of 2 to 5 in comparison to level 1 cache for the level 2 cache, and in memory there is a factor of 50 to 100. This is even true for the high-end CPUs. So an Intel Xeon is not any faster than this. So this is truly something that you have to remember and that you have to work with. Okay, let's keep this in the back of our minds. The next thing that we want to do is just finding an element, an arbitrary element. So we have a collection of elements that may be sorted, of course, and we just want to find an element in this. The benchmark is, of course, not designed to find a single element. This would be, again, too fast. So what I'm doing is I have n elements, and I just have another, I have to find a search order. Okay, first pick this element, then pick that one, and then the next one. And I'm finding all of them. So, of course, I will eventually search for the first element, but I will also search for the last elements, and of course, most of the time I will pick something from the middle of the container. Yeah? And of course, I do this a lot of times again And this is the part that I'm truly measuring. Yeah? So I do not search for a single element, but for a couple of elements, and it should average out eventually. Okay, what I'm using here, slight change, I'm using an unsorted and sorted vector. Yes, a vector can be sorted too. So just to demonstrate that this makes a difference, I'm using both versions now. Okay, let's start with the set though. Because a set, classical container, is the one that should perform best, right? You choose a set if you want to find an element, because this is what tree-like data structures give you. And the big O notation gives us basically the reason why we should use a set. So it's difficult to start with nothing, so this is the performance of the set. All right, let's estimate what the performance of other containers is in relation to a set. Note, however, this here is only for a very small number of elements, just 100. We'll go beyond this in the next slide. Unordered set, sorry.
Are you really using a standard set which does a sequential search on a set? Those has to do something tree related.
So I didn't do a sequential sort on a set. I used a member function. So this is truly the okay, thanks.
This does look like log n, that line.
This is the first part. We'll see then that eventually, so wait till we go to a lot of elements. Yeah, this is just a small set. Unsorted set, unordered set. Okay, what's the estimation? Do you think this should perform better? Yeah, so who thinks it should be better? Okay, this is about a third. Okay, the alternative is it should not run better. So who thinks it should run worse? This is about another third, and the rest thinks should be about the same. Yeah? It's about the same. Yeah, it's just 100 elements. But truly, I can not really gain any advantage from an unordered set. Unordered set, yes. List. So a list is most probably more expensive, right? How much more expensive is it going to be? I think it's about a factor of 2. More expensive, so let's say a factor of 5. Okay, this is about 3/4. So a list is truly something that you do not want to use, right? So regardless of whatever factor you have, you don't want to use it. Yeah? It's not sorted or anything, doesn't matter at all. You always have to start from the beginning because you cannot arbitrarily jump randomly jump to a specific node. You always have to start from the beginning. This is just very bad for performance. Okay, an unsorted vector. Now this is interesting. It is not sorted, which means we always have to sequentially search for the element. But it's a vector. All the elements are contiguous to each other. We load a bunch of elements, and we can probably, it's an int, quickly compare them. So do you expect the unsorted vector to be faster than a set? Yes. Okay. No. Okay, much more yes. So about 2/3 yes, 1/3 no. The unordered vector, unsorted vector, no, not a good idea. So this is, okay, not too nice to see. So if you really a very, very, very small number of elements, it's actually not so bad. But as soon as you have something, let's say 10 elements, it starts to grow. Yeah, it's just not a good idea. However, a vector can be sorted too. Okay? A sorted vector, is this truly a revelation? Does it perform better than set? Who thinks this is something that should beat the set?
What kind of set are you using?
Sorry?
Are you using binary search or still just...
No, of course. Okay. In the case of a sorted vector, of course, use lower bound. Yeah, so it's truly the logarithmic search approach. Yeah? Lower bound. Yeah, exactly. Yeah. Okay. Who thinks this is actually better than a set? Okay, this is about half of the people. And the rest says, no way. A set is just the container for searching elements. Basically no one. Okay, and the rest is undecided, which is okay. Not trusting your gut feeling anymore, I see. So, the sorted vector doesn't show any advantage in comparison to a set or unordered set. So a sorted vector has basically the same performance. So measurement inaccuracy, yeah? You don't gain anything here. Question, yes?
Can it be different from an unsorted vector if we're just searching sequentially?
We're not searching sequentially. So this is, as I said, binary search. This.
It is binary.
Yes, it is. Yeah. However, it doesn't give us a lot of additional advantage, although it's only 100 elements. Okay, there's one missing, a DEG. I just use a sorted DEG. What's the expectation? Would you just say it's just basically a vector? We should have the same performance as the vector? Okay, who says, no way, we've seen the traversal stuff. A DEG is not as fast as a vector, so it should be more expensive. Yeah, okay. A DEG is something that you probably also do not want to use for finding an element. Yeah? Even if it's sorted, and even if it's random access, it's just not working. The problem is that there is a lot of computation involved with this random access. Yeah? You can deterministically say which element you want to access, but unfortunately, you have to do some calculations in order to get there. It's not just an index access as it is in case of vector. This is expensive. Okay, this is just for 100 elements, small. If you go to 1,000 elements, then it suddenly gets interesting. Because about, well, 220 elements, the unnoted set really starts to give you a real advantage in finding an element, right? Both the set and the vector just show that there is a higher complexity involved. Interestingly, the set does not perform too well. So if you just have C++98 or 03 available, whether you choose a set or a sorted vector is not so, doesn't really give you much. If you have C++11, however, definitely use an unordered set. Yeah? That's the message here. If you want to find elements and you have a fair amount of elements in your container, the right choice is definitely an unordered set, not a set though.
Do you have any explanation for the growth of the vector?
For the?
I mean, it looks a bit like exponential growth. And if I'm doing a sequential thing and the CPU basically just reads one cache line after the other, I would not expect that. I would expect that it's linear.
So to some extent, I have to scale it even more to really see if it's now linear or exponential. So
The unsolved vector.
the unsorted, sorry.
Looks like exponential.
Okay. Simple benchmark. It looks like quadratic, that's correct. Yeah, of course, because I'm not just finding a single element, because I'm finding n elements. Yeah? I do this a lot of times. Sorry, I should have pointed this out again. Okay, message here, unordered set is the best container if you want to find something. However, if you are below 200 elements, then using a sorted vector is not a bad choice. On the contrary, it might be much simpler. Yeah? Okay, I know what you're thinking. Well, a sorted vector costs something. A sorted vector, of course, I have to sort the thing first. So there is an additional cost that I did not measure here, and this is building the data structure. Yeah? Inserting all the elements and then doing the sort. Let's just take a quick look at what creating a sorted collection actually takes. So this one is easy. I have vector deg, whatever data structure, I insert n elements in a specific order. For all containers, it's of course the same order, and then I do a sort in case of vector, in case of deg, etc. Of course, not in case of a set. The set is automatically sorted. Yeah. Okay. I did a variation here. One benchmark shows you I use a reserve. The other one shows I do not do a reserve in case of vector. And oops. Of course, do this several times, and this is exactly what I benchmark. All right, let's start with the set again. Yeah? So a set is something that is automatically sorted. You don't have to care about the sorting yourself. It's done automatically. But, disadvantage, when I add an element, it is immediately put at the right position, which means that it's immediately sorted. Yeah? There's no... Yeah, so this invariant of being sorted is always upheld. So this is the performance of a set. Yeah? It's not necessarily the best performance, however. Unordered set. Now this is interesting. I cannot directly sort it because it's unordered, yes, but what do you think? Creating a same collection but not using a set, but an unordered set. Is this a performance advantage or is it not? Who thinks it's definitely better? Okay, about 1/3. Who feels there's also some cost involved? Every single element has to be allocated on the heap. I have to uphold and maintain some governing data structure that gives me quick access, so the buckets. Who feels it's at least as expensive as a set? Okay, this is about the other half. So it is about the same performance as a set. The main problem is, of course, you have to allocate every individual element. Yeah? And it's a list-like implementation internally. And of course, this is memory inaccuracy. It's kind of the same. A list. So yeah, the list is sorted too afterwards. So is it more expensive than these two? I shouldn't have stressed the fact. Okay, and still, who believes, just for the formality, who thinks it's a little faster? So, okay, one true believer of list. It's a little faster, but okay, not much. It's about the same. Again, the problem is basically the same. You have to allocate every single element on the heap. This is the main source of complexity. Okay, now I use a vector. I do a reserve. Standard vector, I allocate all the memory up front, I add all the elements, now afterwards I do a sort. Okay? Is it faster? Okay, this is virtually everyone who thinks it's about the same performance yet again. Okay, so vector is down there. This is a factor of 15 in comparison to the list. Huge difference. And it's about the factor that you see because of all the memory allocations. Yeah? One allocation up front, everything is added nicely, so this is something that goes very quick, and I just have to sort it. Still, it's more than a magnitude, order of magnitude faster. So there is one thing missing, a vector that does not do a reserve up front. Okay, now I have several memory allocations, probably. We don't know that there's a growth strategy involved, but it's probably, most probably not a single memory allocation. No, it's not as fast as the vector with reserve, but what do you feel? What's your gut feeling? Is it closer to the vector? Okay, most, or is it closer to the list? Okay, a few, so about 2/3, 1/3. Sorry, factor 17 to the unnoted set. This is the vector without reserve. There's barely any difference. If I do 5, 6, or 7 memory allocation, doesn't matter in comparison to 400 memory allocations of the other data structures. So, if you know that you have 400 elements, if you can reserve something, great, you gain a little bit. If you cannot, not such a big deal in comparison to choosing something that is node-based. Okay, there's one missing, a DEG, double-ended queue. I just show it. It's very close to the vector without a reserve. It just has a couple of more memory allocations, but definitely not as much as the other data structures do. Yeah. So remember this, building a sorted vector is definitely way faster than building any other node-based data structure sorted. So the set is particularly expensive. And Unnoted set isn't better in this regard. And of course, the same is true. I just want to show this if you have a larger number of elements. So this just goes on and on and on. Eventually, Unnoted set is more efficient a little bit than the set. But, well, it just, so vector is still the data structure that you get quickest if you want to have a sorted data structure. Okay, let's get to the next one. Removing an arbitrary element means I just pick any one of these and I remove it from the collection. And of course, well, I want to do a benchmark. So erasing a single element is not giving me a lot of, so I cannot hardly measure it. So I basically decide I remove all of them. I start with a collection of n elements, and one after another, I remove all of them, but in an arbitrary order. Yeah, I can pick any element first, any other element can be second. Question.
Does order in the removal of from vector has to be preserved or not?
Sorry, once more.
Does order in a vector have to be preserved after removing element? Because it makes the difference.
So I cannot influence this. So the question was, is the order preserved after I remove an element? So,
Because I can swap with last element and do faster.
that's true. So in this particular benchmark, which I show you right now, what I do is, well, I first initialize this in a specific order. Yeah? All the containers are initialized in the same way. Then, over all the elements, I first pick an element. I have also a specific remove order, which is not, of course, the same one as this init order. I pick this one, I find it first, and then erase it. So I do not swap anything. I just call erase, and I'm interested in what the performance of the container is. Yeah? So, of course, I do this a couple of times, yet this initialization part is something I'm not interested in, so the timing goes in here. Yeah? So, of course, I add all the time stuff. Okay, and this is something that, theoretically, lists should be particularly good at. Removing an element, sorry. You're spoiling all the fun. So, a list is a data structure that gives me ON, so big O notation, O1, I'm sorry. O1, when I remove an element. And also Scott says, if you want to remove something in the middle, use a list. So this is why lists should perform very well. I have a sorted list. Yeah? I start with this. This is the performance of the sorted list. Yeah? And an unsorted list doesn't really make a difference. Not really. Yeah? A little more expensive. A standard set. Would you think, well, a set should actually perform better. So, as he stated, I have to find the element first. I cannot just randomly jump to a certain position and erase it. I have to find it first, and set was better in finding things. So doesn't this make a difference? What's your gut feeling? Better? Okay, about half. Basically the same performance. A few, and it should perform worse. Okay, also a few. Well, up to 400 elements, so up to 300, I cannot really tell the difference. Then it seems like set is actually gaining. I will see that this is a performance gain that it will keep for large amounts of elements. An unordered set, Okay, this should be simple. An unknown set is faster. Close to everyone. An unknown set is essentially the same as a set. Okay, a few. It's better. Not a lot better, but it's better. So the unordered set is definitely, so here with a very small number of elements, it doesn't really pay off to use it, but it pays off for more elements because I can find the elements more quickly. Okay, and now come the really interesting containers. Vector. I have an unsorted vector and I have a sorted vector. I want to arbitrarily remove any element in the vector until it's empty. And you know what this means? I pick an element in the range. This element is removed, and everything that's behind this is just shifted. Yeah? So the gap has to be filled. This is something that does not bode well for vector. This is an additional, pretty expensive overhead. Right? So, what do you feel? Sorted or unsorted? Does vector actually perform better than a set? Okay, 2 persons. And who feels no way? So it's definitely more expensive. So the majority, right? So your gut feeling is definitely don't use vector. Vector's down here. Vector is actually very efficient in this benchmark. Yeah? Yes, I'm using an int. An int is a primitive data structure, something that a machine can work with very efficiently. But this is basically the point that I want to show. Up to 400 elements, the sorted vector is just the master of removing at an arbitrary position. Yeah? Of course, the unsorted vector is not as efficient, but still it's better than all the others. Of course, I need more time to find it, but apparently this shift operation is very cheap for up to 400 elements. So if I go, okay, I spoiled this one. DEC is a little more expensive, but still it's to some extent better than the classical containers that you use for this task. So better than list, set, etc. If you go to more elements, 3000, does the game change? Would you still use a vector who says yes after this slide? Okay, and who says eventually a vector just has to degrade in performance? Okay, that's basically everybody. Great. Yes, at some point, of course, the vector degrades, but it's only the unsorted vector. Look here, 3000 elements, and still the vector is kind of leading the pack. Yes, it's very tight, very close to an unordered set. This is because an unordered set is basically the better data structure in finding things, but shifting does not really seem expensive. Only if I go to very, very, very large containers, this is when, of course, the performance of vector will explode. Yeah, of course. If you have very large collections of elements, if you want to remove something in an arbitrary position, then use something like an unordered set. Yet again, yeah, an unordered set is great in finding the thing, and you can quickly remove it. Shifting a couple of 100,000 elements in a vector is not cheap anymore. But I go back one slide. Up to 3,000 elements, it's actually the data structure that you should choose, interestingly, for an int. If you have a different data structure, so a different element type, you should probably benchmark first. It's probably not 3,000, right? Okay. Now we say, well, a list can, of course, not perform well in this benchmark. Well, we have to find the element first. Let's be fair on a list. Let's remove the first element, right? So we don't have to find the element, we just have it right away and we remove it. So basically the same benchmark, with the difference that after initializing it, I just always remove the first element, right? And I do this a couple of times, and I just measure the internal kernel. Yeah? Okay? All right. Let's start with a list. Yeah? This is the container that you should use in this case, probably. This is the performance that a list gives you. A standard set where I also can very quickly access the first element and remove it from the collection. Would you prefer it to list? Who says yes? No one. Who says, but wait, it's actually also node-based. It should be about the same performance. Okay, this is about half. And who says, no, no way. So if I remove always the first element, I have to eventually rebalance my tree. So more than half, which adds up to 120%. Great. So yes, it's more expensive, of course. Yeah. This is from a node removal point of view, it's the same, but eventually I have to rebalance. And this is an additional operation that we can also not influence. We cannot tell now rebalance, please. So yes, it's more important because there's more overhead. An unordered set. Okay, you remember, basically it's implemented as a list internally. But yet again, there's some overhead. Yeah? So an unordered set is also more expensive than a list. It's even more expensive than a set. So keeping all these governing data structures, that the bucket's up to date, is apparently, in this particular implementation, even more expensive. All right, and here comes the big loser, standard vector. Because, of course, if I always remove the first element, I always have to shift everything, right? All the elements have to be moved by 1, so by 4 bytes in this case. So, who would still use a standard vector? So apparently I'm doing a good job here. So, the advice, use a list if you want to remove at the front. So if you have the element, remove it, is not as good. So factor of 5, I think this is huge. Shifting in elements, yeah, it seems to be far cheaper than actually using the delete operator. Oh, question.
Are you sure it's actually shifting? Because in this case, it might just advance the begin pointer. It doesn't have to do anything.
Potentially. Yeah, but this is, again, an optimization that could be done internally. You're right. I'm not aware if this is truly done. So the remark was that you could advance the begin pointer instead of shifting. I believe it's shifted, but I cannot say for sure. I don't know. Okay, so this is, okay, I'm missing one container though, deg. The double-ended queue. Is this something that you feel, well, it's vector-like? And what again was the theoretical advantage of a deg? Ah, yes, I can insert and erase at the begin and end. Yeah. So, what do you think? Vector-like performance? About half. List-like performance? About the other half. It's actually vector-like, very vector-like. Yeah. Perhaps you see this here. It's even a little better. At 200 elements, a little. But 200 elements is just a very small number of elements. Yeah. What happens if I go beyond that? Let's choose 5,000 elements. Okay, who would still trust in the power of vector? Not so many people anymore. Who would use a list? Who would say, okay, this benchmark is truly governed by a list. List is best. Okay, very few number of people. Who would choose a double-ended queue? Okay, this kind of sums it up. Yeah. Yes, the double-ended queue definitely rules. Yeah, so it becomes better than a vector here, and it will stay the best choice kind of forever. List, okay. Agreed is number 2, but with a huge factor in between. And of course, eventually, vector will just lose, unfortunately. Yeah, so you cannot just always use the vector. All right. A short summary. I promise you, we have to come up with something better than just these theoretical decision graphs based on big O notation. So I propose the following 3 if you truly want to, if the majority of operations is traversal of elements, then choose a vector, array, or string. Okay, so I didn't talk about array and string, but it's vector-like, so I think it's fair to just add it here. If this is not true, then if it's movable or cheap to copy, which int is, yes, at this point, if you have a very small number of elements, so perhaps up to 200, a very reasonable choice, according to all the benchmarks that you saw, is to just use a vector, or a string, or array, or whatever vector-like data structure you have. It really doesn't matter if you have only a very small number of elements. Everything else will just add overhead or is not faster. If you want to insert erase at the end, well, basically use a vector, but there's something a little better from a semantical point of view. This is stack. Yeah, so use stack from an interface point of view. If you want to insert erase at the front, we just learned use a double-ended queue, or queue priority queue if you need an adapter for some reason. If I want to insert at any position, anywhere, insert erase, yeah, then again, I should make a decision about how many elements are there. If I have still a fairly small number of elements, 2,500 approximately, this was what we saw in the benchmarks, then a sorted vector or array might actually do the trick. Yeah, this is something that I come up very quickly. You saw that sorting a vector is something that works very well, and no other container can beat the lookup performance. However, if we have more than this, definitely you should use an unordered set. If you need to find elements somewhere, use an unordered set. Yeah. So again, of course, this is successive. So if first this decision, then this decision. If nothing is applied yet, if you're still at no, and you need to find elements, use an unordered set, which means you don't want to traverse it very often. Yeah, so you've already excluded this. Then unordered set is the proper thing. And something I didn't show, if you want to merge or splice very often. So if nothing has applied yet, but you want to merge and splice collections, then probably the list is the right data structure. So note one thing, this kind of all the data structures that I would advise you to use, set/map does not appear. So in C++ 11.14, a set and map is simply obsolete. From a performance point of view, you don't need it anymore. Performance point of view. So there may still be reasons to use it, but it just does not perform well, and you should keep this in mind. Basically, this is also the example that Scott came across when he was posting a blog. Set and map are just basically outdated in this regard. If nothing applies, do some benchmarking before you use your gut feeling. Hopefully you saw it's actually pretty tricky to choose the right container for the right work. Okay, what I did not show is if you have something that's not movable and not cheap to copy, then we should move towards the node-based containers, of course. We don't want to copy it around very often. If you want to insert, erase at any position, use an unordered set. This is just the right thing to do. And if you need to find elements, also use an unordered set. Else, perhaps this is a reasonable use case for a list. Okay, and who can keep this in mind? Honest answer, so who can remember all the decisions? Not really, right? So I try to compress it. One step, and you should be able to remember it fairly easily. If you want to traverse it, or if you have a small number of elements, use a vector, else benchmark. Okay, and this is it, and I'm open for questions. Thanks. Yes, question.
How much data is the custom allocators on those containers using dynamic allocation?
So the question was how much effect would some kind of specific allocator have on the containers that use heap-based allocation, so node-based containers. It might have a dramatic effect, of course. I said this in the beginning. I cannot take this into account. I only have 1 hour, unfortunately. If you have a specific requirement, for instance, you need stable nodes. which is fairly reasonable, fairly good reason to use a list. And you can combine this with some kind of memory pool via an adapter. Probably great choice. Yeah? So it might have a dramatic effect, a positive effect. Yes.
I want to return to remote first element scenario. How can you explain the fact that performance depends of number of elements in the list?
So the very first benchmark, traversal of elements, right? Remove the first element. Okay. So, okay. I should probably go to the slide, and it's probably easier to discuss it. So remove the first element, right? Yes. You're interested in the final performance. This one.
Yes. Why remove first elements from the list depends of number
So, okay, I do not just remove one element, I remove n elements. In this case, at this point, I remove 5,000 elements from the list. Of course, this, as I said, it's very difficult to actually measure the deletion or the removal of one element. The time is in the nanoscale, so cannot be measured accurately. My choice was to just remove all the elements in all cases, and so of course this is a linear complexity. Yeah, question.
Use the microphone. Intrusive data structures are said to have advantages when it comes to performance. Did you consider them, or did you just focus on standard structures? And
so, since you start with this, so of course there is specific data structures. For instance, Boost offers something like a flat map, flat set. This is of course a reasonable thing. So basically this is a lecture from these performance results. For this talk, I just focused on the standard containers. They're used much more often than anything else. If you have something else, something that you feel is better in terms of performance, use it, but don't forget to benchmark first. The message here is benchmarking is actually important. Our gut feeling is not as good as we want it to be.
okay, I think especially for the list, it would be very important to also compare the intrusive version.
That's true, yeah?
Okay. Thanks.
Yes.
Yeah, hello. So first, thank you for this benchmark. So in my daily life, I don't have time to benchmark each time I use a container. And so I use mainly two containers, vector most of the time, and a set when I need, because it also carries information that container is sorted and there's no risk to forget to sort it because sometimes it happens when you change your code. And according to your work, maybe it's time for me to change my habits and switch from set to an ordered set. Can you confirm that, or?
This would be my recommendation. Yeah, if you have a clear threshold where I say, okay, I need to use this basically just for traversal and stuff, use a vector, and this is used for finding elements, then use an unordered set here.
Usually it's also to having a unique list to make because it's a challenging task to make sure I have no repetition, so I'm using sets to do that task. Can I switch to an ordered set, or to make sure everything?
Now I would say you have to benchmark that since you don't have time, so there's no general answer, unfortunately.
And so obviously a list is of no relevant today.
So I see there is use cases for a list, but they're not in the realm of performance. So you would not use a list because of its performance properties. You would use a list, for instance, because of stable nodes.
Yeah.
Yeah. This here focuses on performance only.
Okay, thank you.
Okay, one more question.
For the unordered set, how much would you think the impact of the hash function has on performance? Or something else happening?
That's a very good question. So this is something I would also have to benchmark first, because I have the feeling that my gut feeling would not be good here. So in case of an integer, it's fairly easy. In case of a string, it's probably very, very complex. I think it has a huge impact, definitely, but how big depends on the data type, definitely. And, well, benchmark. Do some benchmarks. Right. Thanks a lot.